All right, we're going to, it's interesting, I got the notes over here, and I guess it will record the notes on the recording, but it doesn't matter. I'm going to make some comments, flip through a lot of the slides that came with this, the first chapter. I've had some questions. Boy, it covers a lot of ground, but it covers it very lightly. So don't feel when you read it, if you read it, you do have a quiz on it. Many of you have taken, I think it's not too hard to do well on the quiz without necessarily having absorbed the chapter, but it's not a chapter you can absorb. It's a little bit like we're here maybe to study how a particular kind of car works, and it's got a review of the transportation industry. And you've got to realize that operating systems covers a lot of ground. We're primarily interested in this course with operating systems that power servers. Not so much phone operating systems or Raspberry Pis or embedded into machine controllers, though they are all operating systems, and so a first chapter is going to have a lot of ideas. Good way to tell did I get what I needed from the chapter is when you do the quiz, and you get 2 tries at the one that's online. There was also the student site that has some exercises, and if those questions make sense to you, you'll be fine. So lots of things that the chapter promises to deliver on, and it's an important set of topics. Sometimes I take those kind of slides out because you'll get the objectives as I go along. But what you should know, and probably know already, operating system software, okay, it's executable commands, really make a layer between you as a user or one of your programs. So when you're using Excel or PowerPoint or even a C# program that you write and execute, an assembler program that you write and execute, a C program you write and execute, those last 2 can sometimes get very close to the operating system and very close to the hardware. But realize that when your program does something, put some text in a file, it's because it said, operating system, I'd like to put some text in the file, and the operating system does that for it. Operating system, I'd like to declare a variable and carve out this part of memory for me, for my program. Then it's the operating system that says, great, and your program can probably find the locations, but the operating system does that. It does that for a lot of reasons, and we'll see them, but really 2, efficiency and protection, security. When they talk about operating system security, they're not so much talking about like hackers breaking in and stealing our database of credit card numbers. They're talking about the security of your programs. Will your program stay in that memory area that it's allocated? Will your program not run amok and steal all our CPU cycles? Will your program not run amok and just fill up a disk with stuff and nobody else can use it? Will it grab and hold resources and not let them go? It's that sense of security that the operating system is about when we talk. And that has efficiency things because it's juggling many, many tasks, and only so much can go on. And with those many tasks, then there is that security element. Also kind of helps with the convenience. I don't know how much low-level programming you've ever done, but just that idea of opening a text file, squirting some text in, and closing it, or opening a file handle, making it, squirting some text in and closing it, is pretty easy. You're going to do it from the command line as part of this next exercise. Writing a program to do it sometimes gets a little, to me, I'm sometimes surprised at the number of steps it takes. You get a handle, you define this output stream, you close the stream, you close the handle, and if you forget some of that, then the operating system kind of leaves that resource open for a while, and maybe when it sees it isn't active, it's done. But I was making the system convenient to use. In a higher level program, it's easy to put text in a file. You could use the echo command at the command line. The lower you go, the harder that gets. There's a lot that goes on. So, the operating system, in Python, you printf or something, and it comes to the screen. That's a convenience. that the operating system provides by making that happen. And it's so efficiency. I would have added this security bit too, in the sense of operating security, system security, but that's what they're there for. If this is a novel idea, then now you've got physical hardware or virtualized hardware. Next layer really is the operating system that's an intermediary, programs, and then the people who use them. That makes up the systems. So the picture, right? Multi-users in general, okay, perhaps not on your device, but it is. I could have other people remoting in to this device if I set it up and we were on a network. I can certainly they should have user one running 2 or 3 things. I'm running probably 100 things right now if I were to look at all the tasks going on my behalf. But if nothing else, I'm running PowerPoint in this recorder right now, and the operating system juggles that. All right, so just, if you will, a hierarchy that leads out to the users and their intent. As I said, so this is general chapter. I was enthused when I got started on it. Okay, I'm going to learn. This chapter doesn't get into any of the how this really happens. Okay, maybe it's the what and a little bit of the why, and so live with it. I don't know that I agree with this, but understand that there are conflicting then demands for an operating system to balance out. If you've has anybody in the room ever been on like a mini computer or a mainframe, an extensible multi? So that's almost archaic. That's how I started way back, in the 70s and in the 80s. We have servers now, people remote in and you have multiple users, but the origin or the birth of operating systems came when you had very expensive hardware that you wanted to take advantage of every cycle and every capability that it had. So the idea that we spend many cycles getting a nice GUI, graphical user interface, waiting maybe for some random input, waiting for the user to wake up and tell us what to do, is an alien concept in that mode. Well, we're kind of a different sort of thing. The hardware, it's not quite throwaway, but it's very much cheaper relative to kind of the software that goes. So the resource utilization hasn't kind of necessarily disappeared, but it is a minor player relative to maybe that security aspect and juggling aspects of what the computer's doing. Okay, and again, there are things like embedded computers and even servers. A true server. Microsoft has what's called a nano server, not to be confused with the nano editor. I meant to mention the nano editor in Linux. You have some examples of using it, but I haven't really talked about it. But the nano server has like one port open. It's got no GUI, and you can, by going in on that port, give it other functionality, but the idea is a server, it just has this minimal surface that gets interacted with, and then what you tell it to do, you open it up, we want it to be a web server or a file server. It starts increasing its capabilities. Other things like a phone, well, what we want is lots of interface, right? And and just hope it all works, and that Android, well, not Android, but I guess it's Google, and Apple can keep it going. So, kind of mention this. Who gets what resources, right? There's one, well, it's multiple CPUs, but one set of, computational capability, one amount of memory, one amount of disk, printer. So, who gets what when, and can I do that efficiently and, quote, fairly, and worry about that security or improper use of the program, or they haven't done what they should have. I kept this slide. Well, I'm really going through them all, so there's no universally accepted definition. I guess that's a good thing. It's what you get when you turn it on the first time. But a concept to start getting your head around is this idea of a kernel. Okay, Kernel, and it's kind of meant to be that core capabilities of what a computer can do without any support from programs that get loaded in. So we're going to talk about environment variables and this path variable. What I did was just look at it. When I type a command at this command prompt, like I did a CD, all right, that command, okay, is either residing in memory of the computer, what's called and I would call that the kernel, what's residing in memory, or when you type in a command name, the computer, the operating system, goes down this list of locations to see, can I find that command? And if I can't find that command, then the operating system tells you that, okay, that's not a valid command. Now, there might be a bogus exe somewhere on this computer, okay, but it's not in this folder or it's not in the path, and so the computer kind of didn't give up, said, I can't find and help you with this. And so this path environment variable helps supplement where the computer will look to bring in programs and load them. And this is, it's very, ls is a Linux thing. Yep, doing it again. And so, the many programs that are out, say regedit. Regedit will let you edit the registry on a computer. The registry on a Windows computer is sort of a database of values that the operating system keeps to know maybe some of your preferences, where things are located, and that kind of thing. So regedit, because it's an exe, is not part of the kernel. If I do type regedit, regedit will do something, but it will do something because it loaded that software off the disk and then executed it, just like any other application. So you can find out what's in the kernel if you want. That's not so much the point as it is to realize it's what gets loaded into memory when you start your computer, and everything else is a system program like regedit or an application program like maybe Excel or PowerPoint. So, and I'm kind of waving my hands funny. That's okay. That's nomenclature, and you might be well used to it. And if not, that's what this first chapter is about. But it is, as I say, kind of this level. It doesn't tell you how to recompile the kernel and who decides what goes in the kernel and can I add to the kernel. You could do those things in Linux. You can't do those things in Windows, right? Why? Linux is open source. Windows is proprietary. Right? So Microsoft says we control. Now you can extend the operating system with your own EXEs in Windows, but you can't change the kernel. But in Linux you could. All right, you hear about booting up. Booting up is called booting up because it's really short term for bootstrapping and the idea of tying your shoelaces, right? And, just bringing them on. You should know that every computer has some firmware. Okay, that holds the instructions when you first kick your computer on. The CPU needs to get its code from somewhere, and it gets that code from, it's sometimes called the BIOS, basic input-output system. They kind of come with a UEFI, and we'll look at the difference in these in a couple of weeks, but the idea is there's some firmware that does, why is it called firmware? You can change some of these. Very early in the course when I said make sure your Windows PC can be virtualized, that setting is something that's in firmware. So you can, before you boot up, go change those properties and allow it to or prohibit it from. You can put a very low-level password in it if you want that comes. And so kind of think of that as the first, then the bootstrap program gets some stuff in memory, and then it tells the computer, the memory, well, here's where you get the rest of your stuff to bring in to have available. All right, so we know that CPU, central processing unit, sometimes there's multiple in their cores, and Can't think of much to add to this. The idea of concurrency, managing the variety of devices. Realize that most devices have some controller that's in between the operating system and the device. The way when I type a character that it appears on screen is not because my keyboard is connected to the monitor in any way. It's because the operating system is polling and looking at the device controller for the keyboard. When it sees something in a particular area of memory, it says, well, what do I do with this? And most of the time, like when I'm in the command window, it says, oh, what the user wants to do is see that on the screen. You can be in some programs and you type characters and nothing happens because the program is controlling that for you. All right. When you get deep into operating systems, this idea of I/O devices and CPU going concurrently is one of the critical issues. This one doesn't say it here, but usually the CPU is blazing fast compared to how quickly it takes certainly to put something on the monitor, even to store something in memory, much less have it go out to printer or over the network on the internet. So you kind of have this like idiot savant, the CPU that's just got spinning with all this capability, and it says, okay, put this character on the monitor. Eons in terms of CPU time go if the CPU just said, I'm going to wait till and freeze everything else till I get back confirmation that that thing's gone onto the screen. The way it really happens is, and it's in terms, the term is an interrupt, okay? The CPU will say, my job is to have this on the screen. I'm going to go do something else now. And then that monitor controller, when it gets onto the screen, says tap CPU, okay, that's done. And then the CPU, depending on where it is, will get around to doing something next. But device controllers let the CPU, it's time to do something else, go. And that's called an interrupt because the idea is you'd like the CPU not to be frozen, just wait, or spending its time looking. And so it's it's a beautiful thing. So some things about the interrupt vector. Think of that as a list of parameters, like when you pass parameters to a subroutine, like in C#, and it's kind of here's what go and addresses, and it's a and there are traps waiting when X happens. We want to grab it. An exception is something that we didn't expect to happen happened, and all of those are different ways to tap the operating system and wake up and do something about it. And for the most part, we see it, not even in, we don't see it, right? It's happening for us as a benefit of having the operating system, looking at the code and how it manages it way deeper than we're going to get to, though we'll look at a couple of things, okay? We really don't need to, sort of a polling is, I am going through a cycle. Is this done? Is this done? Is this done? Is this done? That's a polling interrupt. A vectored interrupt is more pushed to the operating system, saying here's some values and do some things with it. And I never quite could, but I left it. Just the idea that the I/O device and the CPU, will sort of alternate their working, and it's the interrupts that get the CPU then to wake up and then do something with what's going on. So they're not linked, they're asynchronous, and on it goes. And in fact, here's a slide where I just kind of talked about the idea that the CPU kind of has to do something, and we like it to use its time effectively before going on to something else. System call is when somebody calls into the OS. I'd like to put some in a file, something on the screen, and right. Oops. It was talking about indexing. it just is an efficient way to keep track of what's going on, and really more detail than we need now. You should probably know all of this. We talked about bits and bytes. Sometimes a word is used for a byte. Yeah, and I'm trying to think. You know, sometimes a kilobyte, people round off to 1,000, right? Because it's ironic or just a coincidence that, you know, the 2 to the 10th, is it? Which is a kilobyte, is about the same as our 10 to the third, and so it's 1,000 is near 1,024, and so sometimes you'll get a disk drive and they'll talk about its capacity, maybe in gigabytes, but they're using gigabytes when it's 1,000 rather than 1,024. But just yeah, something you're familiar with. So the main memory of a computer, you know, random access means any spot can be retrieved without having to go through the others. I don't think you see much serial access anymore. Go ask your grandma about a cassette player or something. That's probably a good example of serial access. If I want to get to track 3 and I'm at the start of the tape, I have to fast forward between tracks 1 and 2 to get 3. But on a CD is direct access or random access. I can get any spot. Another fact about main memory, which is why we save our files or we have autosave and those kinds of things, it's volatile. Volatile means it needs electric power to remember its contents, and so when the power goes out, say on a traditional computer, or the battery goes out on a laptop, everything we're doing on the computer is gone. If we saved it, we're good. Or if it was auto-saved for us, put down to permanent storage, secondary storage, and it's non-volatile, a disk will remember what's going on. I don't know if you've ever been through how a disk drive works, but it's almost like platters, look like a stack of record albums or something, but the data is transcribed to the media that's stored there. Disks can be a little bit, if you like jar them or you drop, and it's got a traditional hard disk, you can have a head crash because there's this little pin that's kind of reading all the data, and that things have gotten better than at that. More recently, there's the notion of solid state disks. They work a little bit more like memory, and faster, getting cheaper. And probably the way to go for this one, computers. For the main drive of a computer you buy today, you want to get that. So they're kind of talk about the hierarchy of speed, and you're familiar with registers. We haven't really talked about a cache. Cache is a temporary location that is maybe on its way, but in our experience with the assembler, we got used to moving things, or at least saw in and out of registers, and you saw the main memory. We couldn't see the fact that if register to register would work much faster than register to memory or memory to memory if you were going to do it. That simulator doesn't get it at that level of detail. We talked about solid state being better than hard disk, more expensive, but better in terms of quicker, probably a little more reliable. CD or DVD would be next. And I don't know if anybody in the room's may have seen a magnetic tape, but it's one way to store and kind of a legacy way to keep information. And all you can think of a cache as a holding area, almost like a buffer. It's a temporary holding place. So the CPU can say, here, I need to write this. You need to write all this to disk. Here's a kilobyte. And I go on to do something else, and something else is taking that byte by byte and moving it down. And so there are times you can run into this when if you're shutting down or pausing your VMs, make sure that gets all the way paused before you close out of VMware, because a lot of those writes, whatever was going on in that VM, were cached, and it takes a while for that to get written to disk, so it's permanently stored. So it's no joke that cache management, it is an important design problem. We're here not to, well, how did they solve that problem, and how do I know if my caches are right, but just realizing that it's there. Sometimes it caches instructions on the input. It compiles ahead and anticipates what the next instruction that's going to be loaded is, and that turned out to be the source of one of the flaws that in VMs you can get a cross the CPU, cross cores hack if it's done cleverly and correctly, but that goes on. So direct memory access structure, yeah. Transferring blocks of data. So sometimes when you think, gee, I'm going to get, I need a specific item, or you conceptualize that the CPU just needs this one particular value, well, typically a whole block of data, some amount is all brought in, and it's sorted out, and the piece that it needs is taken, rather than going to get that just that it gets that specific one. It's still direct access or random access, but that is the notion. I'm not sure that there's much else that I get from this particular diagram, other than the idea that instructions and data occupy the same space. They occupy memory. They're in binary, and it's the CPU that's making the distinction, and the cache acts as a buffer then for what's coming in. All right, yeah. So we have multi-processors. Most of you had 2 cores, 4 cores on your machine. They're symmetric multiprocessors, at least the ones we have. Symmetric just means the CPUs are all the same. The cores can do all the tasks. Some have asymmetric multiprocessing. You might think of the asymmetric multiprocessing a little bit like the difference between your CPU and your monitor controller or your disk drive controller. They're both computers, but very different. And more cores means more horsepower. Also means a little more work for the operating system to keep things going on. So it's interesting that they do 3 of them here, because they usually don't come in 3s. They come in powers of 2. You have 1, you have 2, you have 4, you have 8 processors. But that's the idea. They share memory, but they have their own onboard registers and cache. There's a notion in most of the computers, your PCs, any kind of recent last 5 years, a chip can have multiple cores. So you can have multi-chip, and then you can have multiple cores per chip. And so it's just an architectural way to make it have more separate computing resources, if you will, than you would otherwise. And again, the whole idea is just trying to give every advantage for this computer to be performant and still get its work done. And I don't know that we really need to, that's not a slide worth getting into. It's talking about, and they got a picture of it, managing then the storage. Okay, it's called a storage area network, but just drives, maybe file servers that are hooked up, and a way to organize the interplay between the computers and those drives. All right, boy, these are old kinds of systems. Okay, a batch system, that's what I grew up on. You don't see those too much today. Maybe a long-running process. I don't know if you've ever put a video up on YouTube or something, but you upload it, and it goes through where it uploads it, then it processes it, and then it makes sure you haven't violated copyright, and does some other things. That's kind of like a batch process to us. I kick it off, and I wait for the result. Okay, and it's not something. Then nice thing is you can go do something else while that's going on. Used to be that's all you could get out of computers, and maybe you give it a deck or a program, and it does the job, and then you kind of see the results and react to it. timeshare or multitasking, and to me those are two different things. A computer, your phone is multitasking. Only there was one phone that I saw recently. There may be others that really allowed multiple users, but not at the same time. You could have a login for one user and a login for another user. Time sharing to me is sharing time among multiple users. We're going to see that, I think, when you do in TechPrac 1, how you can take your server in Windows and set it up for remote desktop, allowing other people to use your computer while you're using it. And you could have hundreds in there with the right capacity and setup. In Linux, it's SSH, secure shell, but you can have multiple users on one computer, and it's a networking kind of thing. The idea is to have some goals for that. You get too many users, and there used to be this 1 second threshold. We did some performance testing way back. I started out as a programmer doing local government financial systems, and the idea when the user hits enter, they're entering maybe a transaction. Your taxes have come in and they've entered the stuff, and go that more than a second, probably back in those days, several seconds for something like that. But there's this now more than a second, and you've lost them, right? So if you're really trying to have an engaging interface, there's the idea that you need to keep it performant, and if you can cache back up, build up that work to do later that needs to get done, but keep the interface going. That's the way it goes. So each person takes some memory. A couple of things that happened. If didn't realize memory's finite, and you don't have the memory on your computer for all the programs that you're running or going to run. So I think I talked about it in that first video. When you start up a program like Excel, it brings in enough of that program's code to get you started. But sometimes when you're using a program and you hit a new function, this happens in Excel, it's called a page fault. I don't have that page of code. Don't think about a page of written code. I don't have those instructions I need, so I need to go back to the disk to bring that in, but maybe I don't need this part of the program anymore, so that goes, I just get rid of it because I can always get back from disk when I need it. That's swapping, and that's why there's sometimes a delay and some disk activity. That's why the more memory you have, the more instructions you can keep in memory at the same time, and the more performant your computer would be. So that's swapping. Virtual memory is the idea of take some of my disk space and have the computer think that it's memory. And it'll work a little slower, but it'll say, oh, I've got this in, quote, memory, and I can, it will be, I don't have to do a page swap to get it. I don't know if this guy here, if it's, no, I don't know if I've got it set up, or I'd have to work to find it, but I know in Windows 7 and before, you could go look at, you could find the virtual memory. It would be a file in your file system that the system was using. So kind of think of virtual memory as disk space used as memory for convenience. And it just says, kind of each program takes its little slice of memory, and it's going to be that. We talked about interrupts. And, oops. I don't know where I was. And, I might have got a little bit ahead, but not much. Yeah, we were at this guy. Right, so it's a mode that you kind of recognize that a user is doing this, or is the kernel in charge? And when the user is in charge, the computer will check more things. We're going to look at exercise with that in TechPrac 3. It takes a little more time because if you're trying to protect that, check that a program is staying within its memory bounds and its other resource limitations, then you're doing a lot of validation before executing. If you trust it and say the kernel, then you let it go and do what it does without some of those checkings. And so that's kind of this idea of privilege instructions. I heard where Disney is getting away from their fast, or they're going to charge. You get to pay for the fast pass. I don't have to wait in the line. I've paid a little bit extra. I can kind of get by. I have this privilege. You don't have to check that I'm doing the right things with memory because I'm this kernel. That's why you worry when, especially in a Linux, but in a Windows system too, somebody hacks and gets what they call root access. That kind of gives them all more at a user level, all the privileges of the system, and it's problematic. And you're used to this idea of then taking your computer and dividing its capability among what look like separate machines. I was running a Windows server on a Windows 10 computer a few moments ago, and it didn't spin anybody's heads. We've seen that kind of thing before. So this is kind of how I talked about the user process needs something from the kernel. So it says, put something in a file, and it happens, and then it gets back to the user program if all goes well. And if something goes wrong, well, maybe it puts up an error. It was kind of funny. This was years ago, and you might have remembered. I might see if I can find the slide. But sometimes when a program that wasn't programmed correctly got into memory where it wasn't allowed, what would pop up on Windows is your program, or the program has performed an illegal operation, and we've shut down the program. We've stopped the process, something like that. I had a student, it was an MINF class, okay, so I was over in the business school, said, well, that came up, and his mom saw it, and his mom was convinced that he was doing something illegal on the computer, like, hacking in or counterfeiting or something. She didn't know what. Would you please say it's really the program was just, you were supposed to be in this sandbox, and you tried to grab something or put something over where you shouldn't have, and so it, like buffer overrun, we did that a little bit, if you remember in that first assembly thing. Okay, well, you meant to have this area that appeared in the output buffer, but then you started writing output all over the place, basically because your program wasn't well written, and so illegal operation, meaning you're not obeying the rules that are set for that user, not illegal in the sense that the law will come get you. Okay, and I think we have talked through most of this, and we know the program counter as the instruction pointer in that little simulated machine that we looked at, and it's really, that's how, what does the CPU know what to do next? It's going to look at its IP, not the internet type of pointer, but instruction pointer, and that's where I'm going to go, and it doesn't determine, oh, well, wait a minute, that was a data location. Well, it might if it's validating some user input, but that process management is what the computer is all about. Yep. And I could kind of read this, deadlock is two resources or two processes want the same resource, and how to work that out, how to let you know I'm ready and I know you're ready, how to say this one, put it off to the side, I'll get back to it. Realize this happens. There's nothing in here that says, well, gee, how does it do it? Is my computer doing it well now or not? But that's the process management, that kind of memory management. And we looked at that when looking at the task manager that's on a Windows system or similar on a Mac or Linux. We can see what memory is allocated where. We can see it and realize that the CPU has to manage it. And when that memory is full, it starts to throttle, and it doesn't make much progress. But realizing that controlling that resource, controlling the storage on the disks and the file system, and even allocation, that's the third. This mass storage is external or tape drives or tertiary magnetic, putting it on and writing it to a DVD. And got a little graphic. I don't know that it's that helpful about the performance level. Kind of goes from the size gets bigger, the speed gets smaller, and speed gets smaller means the bandwidth, the access time goes up and the bandwidth goes down. And so it does matter. Probably we only see it when it kind of hits the disk from our user perspective, typical like I am here. And we can see how much memory's done, and Task Manager will tell us who's using what. There really is no good way without deep electronics to kind of be observing this. We can simulate it with that assembler, or you get a little sense of it if you're actually doing assembler, but hierarchy of storage. I think I've touched on this. This cache coherency means same value of the truth everywhere. Sometimes there's the so-called maybe dirty read or something. Some other process was changing the hard drive, and you pulled this value, process A, and then process B stuck something down on the hard disk. How does then this process A that's waiting for this to come say, wait a minute, I've got an updated copy, I've got to wait even longer for that to come. Okay, and so that's how to solve it, all the way to chapter 17, which this course really isn't about getting to, though it's a great and important thing. The input, output to get it on the monitor, receive it from the keyboard, understand what the mouse is doing. It's a system into itself. So now we're talking about high-level protection. You should probably know what all those vectors are. That is denial of service, a worm versus a virus. My wife one time was doing something, and anyway, she swallowed a Trojan, and it hosed the computer, and we just rebuilt the hard drive. It was no big thing. But she goes, Trojan, what is a prophylactic? What is a rubber? Means protection. What does that have to do with it? I said, no, Trojan, like the Trojan horse, that you click on something thinking you're getting something, and it's got malware inside. And if you didn't know that, and we are identifying on servers, it's typically and almost always a user ID. Sometimes it's a key or a token that they hold. And the idea of security is put users in groups and assign privileges then to groups. That's kind of a high-level thing. It is an operating system task, but it's operating system more of the application or system software, not operating system down at the registers in memory level. It's but I put it in my chapter 1, talking about how the computer can keep track of data on lists. I don't know if you've had a data structures course or a database course, but the idea of if a user links to a user, there are ways to manage data structures, and this really isn't the course to handle it. Another way to search effectively, if you haven't ever heard of, you should understand that a binary tree is a way to, say I'm looking for numbers and I'm looking for 32, or if it's 30 on the list, then I'd branch right, because that's the branch that gets me there. I don't have to search the whole list. I can search a part of the list, and so data structures are important, but and the operating system is doing it. So made a passing wave at a binary tree. The idea of a hash is, if I have a value, I can come up with an algorithm to come up with a memory location for it, and so I can quickly grab it out of that memory location. Sometimes then there's collisions, and anyway. But a hash map is you take a value, and it's an algorithm that from the value tells me where I stored it, okay, kind of like a code. And so then when I get the value again, I know where to kind of link back to get the stuff that goes with it. Bitmap is just exactly that, a sequence of bits. Can define anything, but usually we think of a bitmap being a picture. Now we are getting very high level, and if trying to think of anything to add. This is, to me, gotten beyond operating systems, so it's in, other than the idea maybe of a firewall. That's system software to me more than OS, but you realize you can control which ports, avenues can come in, which ports and avenues can go out of your computer, and it's an important aspect of the protection. And one thing I had mentioned, just as an example, if you get on guest Wi-Fi on campus, you can't do remote desktop because that particular portal, that Wi-Fi connection, doesn't allow port 3389, which is where it goes. So, yeah. And I would say stuff, and if you didn't know some of this, I guess I haven't dabbled with augmented reality, but I guess Pikachu about 4 or 5 years ago was on campus near the phone, near the fountain, and you could do it there now. Yeah. So the operating system's embedded in a communications network to make it useful. Gosh, today I'm trying to think of what you could do with a standalone computer that had no network connectivity that would be interesting. If you were writing down intents, doing some calculations in Excel, writing programs, testing them, I guess with VMs, but the VM kind of gives you a little network to test against, is getting less and less that you really do functionally, where you kind of don't almost count on having that internet there to give you some oomph. You'll talk about those, or already have in your networking course, and I don't know that the distinctions are all that important. I'm probably familiar with the cloud. All that is a device or a service or capability that we access via the internet. Okay, and so it's a cloud, and we might look at that a little bit toward the end. You get into it if you take the AIST3720 enterprise class, and we really don't need peer-to-peer networks. Virtualization is important. We're applying it here. Yes, it's And somebody asked, does the VM emulate? And it really doesn't emulate. Our VMware doesn't emulate another operating system. You can think of it that way. Gives us the capabilities. We're really virtualizing it in the sense that VMware is more natively using the hardware rather than having software that says, oh, when you do this on this computer, it means this on this computer. It's just saying, here, you have these resources, install the operating system. And our hypervisor is VMware, but you might be using VirtualBox. And examples of what you can do, right? And so kind of that virtualization is very handy for operating systems studies. And this one is really just kind of talking about maybe the difference. And there are two kinds of hypervisors. The distinction doesn't come up very often. A type 1 and a type 2 hypervisor. VMware is a type 1. The actual VMware software runs on our computer, and it manages the separate VMs, so it's got a layer, the VM manager. In a type 2, and Microsoft's hypervisor, and I think vMsphere and the VMware, the entire operating system is built, and the only thing the operating system does, I should say only in quotes, it's significant, is run other VMs. You don't load any software natively. All you do is spin up VMs, but that's getting down into virtualization way more than we're going to do in terms of how it works. And there are different levels of cloud. There's a cloud computing class, and all the asses, as I call them. Am I getting a software as a service? When I do like email, it probably lives out in the cloud. Do I have a platform like a Windows computer infrastructure? Oh, I've got memory and a disk, and I do what I want with it. But that's again above what we're going to get into and looking at, other than realize that there's operating systems at every level of it. So we connect through the internet and I would say that's the definition of cloud. So yeah, and RTOSs. And that's the idea. You need that response. It's a real-time medical kind of thing, right? If it's measuring heartbeat, sending a shock. I go in about a week and a couple of days, Thursday the 2nd for a hip replacement, and so that important that they're getting it within a time constraint, so the next thing can happen. A lot of times numeric controllers on machines, the robots you see painting cars and that kind of thing, are examples of that. Open source means you can see the source code. Doesn't mean it's free, but typically free and open source go together. And Linux and Unix are open source, and Windows is the classic proprietary or closed source example. And benefits to each, more of a enterprise management consideration. Like, gee, I want to set up servers. Should I go Linux? Should I go Windows Server? And there's benefits and curses to both. But finally, yes, kind of some of those last were probably should have eliminated as being beyond. So I will let that in the comments, and let me just stop this.